Welcome to Study Loop.
In this question, a bubble with a diameter of 3.6 cm is released from a depth of 14 meters below the sea surface. So, and the bubble rises up to the surface of to the sea surface, and then we want to find the new diameter of the bubble, assuming the temperature is constant. Okay. So, and then we'll sketch a PV diagram for the process, and after that, find change in internal energy, work done by the air, and also the heat. Okay, Q. All right, so to do this, okay, so we recognize that the temperature is constant, right? So from the ideal gas equation, so from PV equals to nRT. If T is constant, that means P1 V1 equals to P2 V2. Okay, so now we write down what is P1. Okay, P1 is at the initial state, which is P atmospheric pressure plus rho GH. And then P2 is just atmospheric pressure. V1 is the volume of a sphere, so 4 over 3 pi d1 over 2 cube. Okay, and then V2 is 4 over 3 pi d2 over 2 cube. Okay, so now we can put them together. So we have atmospheric pressure plus rho gh 4 over 3 pi d1 over 2 cube is equal to atmospheric pressure times 4 over 3 pi d2 over 2 cube. Okay, so the 4/3 pi cancel out, the half is also cancel out. We are interested in d2. Okay, so d2 is equal to atmospheric pressure plus rho gh divided by atmospheric pressure, and this whole thing to the power 1/3 times d1. Okay, so we substitute the numbers. Okay, so the density of seawater is 1,000, just then 9.8. H is 14, and then divide by 1.013 times 10 to the 5, okay, to the power 1/3, and then multiply by 3.6 cm. Okay, and you calculate this, you get 4.79 cm. Okay. Okay, so this is the answer for part A. Okay. In part B, we need to draw a PV diagram for the process. So this is an isothermal process. Okay. Okay, so just put the relevant terms. Okay. So which V1 is equal to 4 over 3 pi d1 over 2 cube. Okay. So okay, so you can calculate this yourself, and then V2 is 4 over 3 pi times d2 over 2 cube. Okay, so this is how the PV diagram will look like. Yeah. And then in part C, we need to calculate the work done by the air, change in internal energy, and the heat. Okay. So for isothermal process, okay, delta E internal is 0, okay, because it depends on change in temperature. Okay, so and since isothermal process delta T is 0, okay. Next we find W. Okay, this is equal to integral of P dV, and using the ideal gas law, you have nRT over V dV. So and then from V1 to V2, okay, so you get nRT natural log V2 over V1, okay, and then you know that from previous part V1 is like this, V2 is like this, so you can see that the 4/3 pi and the half cube, they cancel out, so you have natural log D2 over D1 to the power 3, okay, or D2 over D1 cube. Okay, and you know that this is 3 nRT natural log D2 over D1. Okay, and using the ideal gas equation, or you can just substitute like P2 V2. Okay, yeah, because temperature is constant, so P1 V1 equals to P2 V2, so you can put P1 V1 here or P2 V2 here, so I choose P2 V2. Okay, natural log D2 over D1. Okay, so you have 3 times 1.013 times 10 to the 5, that's P2, which is atmospheric pressure, and then V2 is 4 over 3 pi D2. Okay, D2 in part A, we found that to be 4.79 cm, so you put 0.0479, then divide by 2 cube, and then natural log 4.79. Okay, in here you can just put in cm, but outside you need to put in SI units. Okay, and 3.6. Yeah, so you calculate this, you get 4.99 joules. Okay, and then from first law of thermodynamics, okay, which says that delta E internal equals to Q minus W. So since delta E internal is 0, okay, Q is equal to W is equal to 4.99 joules. Okay, so in part B, this is the W, this is the Q, and then delta E internal is 0. Okay, and that's all for part C.